Linked list, which is one of our A-level data structures that we need to learn. So remember that lists use data or arrays that are stored contiguously in memory, so one item next to another in memory. Why is this potentially inefficient? Well, I mean, a few examples might be that if you set aside 1,000 spaces in memory, but you actually only end up using 100 of them, those memory slots have been predefined when you wrote the program. We know that with a list, it's dynamic compared to an array, so that actually uses data a little bit better. However, it does rely on data being contiguous. So that means that if there isn't enough memory to expand our list, then it won't be able to expand. A linked list allows us to actually store items not contiguously in memory, and that means we don't need to predefine how much memory to set aside. So it's one of our dynamic data structures, which means it can grow, and it's an example of an abstract data type. If you can't remember what that word means, then please go away and remind yourself and do your research, quite an important term. So here's just an example of what a list might look like. So each item on our list is made up of a node, where the node contains the actual data we want to store and then the index pointer for where the next item would be found. So this is a partial part of a list that tells me that in order to get from oranges, which is the first item, I need to go to index position 2. And then so on. Pears is index position 3 and apples, the next item would be found at index position 5. So this doesn't relate to its index position, but where the next item is going to be found. So then looking at this last one, grapes, this says null, which tells us there is no next item. So null is only found on the final item within our list. Visual example. So we're going to start with this list. We have the index items position at the top. So this is the actual index position of where each item is currently. And below is the pointer. So we think we always start at 0, but we know that to get to the next item for red, we need to include in the node the index pointer 1. So then moving on to the next bit, we've now removed blue, but now I need to make sure that I update my pointers. So green has to now point to 3, where we would find pink, and the rest actually can stay in order for the moment. However, if I now wanted to add yellow in, I need to change my pointers because it still remains the same, and yellow is the end of my list even though it sits higher up in terms of indexing position currently. But this is how we keep that list in order, by using the pointers. So instead now of going from orange to null, orange points back to 2 where I find yellow, and that is now null. So I'm going to give you guys an example to work on. I'm going to give you this original list. You're going to remove purple, black and grey, show the updated pointers, then add yellow and turquoise and show the updated pointers again, remove orange from the list, add mauve to the list, and then show the final pointers and position of every item on the list. If you pause the video now, I want to give this a go on paper, and then I'm going to go through the answers. So hopefully you managed to do that okay. So starting off with the original list, we need to remove black, purple and grey and show the updated pointers. So here we've removed purple, black and grey, and we can see that pink now points to 6, white now points to 8, and so on the list continues. Then we wanted to add yellow and turquoise. Now, in terms of programming this, what you're going to need to understand is that to find the next available position, we would always start at the front of the list and work our way sequentially until we find an empty slot. Okay, because otherwise, if we start here, there's nowhere to go. So it makes the most sense to go that way. So with that in mind, our next item, yellow, is going to need to go in here, and then we're going to update the pointers, and turquoise should go into there, like this. So we're now saying, remember that this pink must continue to point to white and onto beige, but now orange comes back to yellow. Yellow points to number 5, which is turquoise, and that's the end of our list. I'm going to show you another example of this in a minute just to help visualize it a little bit better. Last but not least, I'm going to add mauve to the list and have removed orange, which means that we should be able to follow our list as it is at the bottom. This is how it would appear if we'd written this all on a piece of paper. Red, green, blue, pink. So we know we get as far as here. Pink, 6. So we should have white. Takes us to beige. Takes us to yellow. Takes us to turquoise. And finally, 7 takes us to MOV, and that's exactly as we would expect to see it at the bottom. So just to show this in a slightly more visual way so you can follow the steps through, just remember this is our current indexing positions. So first again was to remove purple, black and grey. Once we've done that, and right here I'm keeping a tab of our list the whole time, we're going to show the updated pointers. So we've now changed them. So before that's how they were originally, and we've changed them. So we can see that. Then we're going to add yellow and turquoise. So we've done that here. And then we need to show the updated pointers. So we've changed our pointers round. Yep, and then remove orange from the list. Orange is gone. And then we need to add a mauve to the list. So remember we've updated beige now to be the final thing to point to yellow. We should find that this list is matching perfectly. And once we've added that in, we show the final pointers. And so what we can see is this is our list as we would expect it. That is the order in which we appended things. Right now we haven't looked at adding and replacing and removing. We've just looked at appending items, adding items as you would with a shopping list to the very end of this list. But this is what it looks like in terms of the way that it's been represented, because actually these could be stored anywhere in memory and we just know where the next item is going to be found. So what I'm going to get you to do now is you're going to be doing some research in how to add items, remove items, and also search the list. So your task is going to be that you are going to, there's plenty of books and resources out there, plenty of other videos, and the next lesson I'm actually going to show you some of the answers. But you're going to look at how you're going to add items to a list. I'm going to give you a worksheet with a couple of tasks to do, and then after that you're going to go away and find the pseudocode for just at this moment adding an item, and we will look at the others before. You're going to see this term come up a lot, which is traversal, traverse. And the idea is that when you traverse through something, it's searching every single node, normally in reverse, but also you can traverse forward and backwards. So it just means searching every point of a list. And in order to search a linked list, we must search every single node to find the item we want. Talking about pros and cons, it's a very good point to say that we've talked about the pros. One major con of a linked list is that, one, we could run out of memory and we wouldn't be able to add any item, and we wouldn't know that until we tried to add an item. But also we can't directly access the index position of any given item. We need to traverse through the entire list, which means if the item we're looking for is right at the very end, then it's not going to be that efficient. However, you will see that linked lists themselves actually become part of other data structures, and there's a place and time for all of them. So I'm going to set you a few activities. Hopefully you can go through this video again if you need to, and you're going to, by the end of this week and early next week, be able to program a linked list.